we talked a little bit, even though we're not into the speed sensors yet. We talked about one way that we could get the speed off an encoder, an incremental encoder, which is, y'all know, we got quadrature encoders and an incremental encoder. So what's the difference between those two?
Speed and position.
We can get speed and position, but we can't get direction. So we can use these on anything that don't require direction. Then we have a quadrature encoder. What does a quadrature encoder give us? Direction, speed, and position. In fact, I've seen applications where they use a quadrature encoder, even though it's got an incremental application. And what they do is they count the rise and edge of both inputs. And that way, it would double the resolution of the encoder. You understand that? So the resolution of the code. What is resolution? I should put that on the test too. I need to write this down and come back. So what is resolution?
So many dots.
Pixels.
Yeah, you're giving me examples of resolution, but you're not telling me what resolution is. The preciseness, how precise it gets. So if I had one slash on my encoder, then I'd only get 1 pulse per revolution. And I come up here and turn it, and I stop it somewhere in the center, I'd have no idea where it was at, right? You understand? Because I only get 1 pulse out of every revolution. If I add 2 dashes, then my resolution would double. If I had 4, it would quadruple, right? So the more lines or the more indications that we get on our encoder, the more resolution it has, the higher the resolution. So I saw encoders that had over 2,000. I think I saw one that said they went up to 25,000 dashes per revolution, which is what you would see if you ran into a robot, right? These robots that we have that use these encoders have to be extremely precise. So their encoders will have a lot of resolution, a real high resolution. So we have a encoder, and let's just make up one. One that I looked at, it had 64. So it did the pulses per cycle, per revolution. Okay. So what would we do with that? So I'm going from pulses per revolution over to what? Speed, and what's our speed in? RPM. The way I go from 64 pulses per revolution over to RPM would be the transfer function. That would be the transfer function. Now, if I was measuring this with an oscilloscope, and then I measure 20 milliseconds, then what would be the speed? So this is what we call the period. So I'm getting, that's the period, yeah. So if I was measuring the pulses coming off this encoder, then the time here would be 2 milliseconds. So what'd you say, Jerry?
What did you
You
ask?
sound like me. What would be the speed? We can do this couple of
2 milliseconds per pulse.
2 milliseconds per pulse.
And 64 pulse.
Per revolution. So yeah, first thing we would do, and we could do this several ways, but I'll show you both ways. So that means I would take 2 milliseconds, and then I multiply it by the number of pulses, and then this would give me the pulses per revolution. So what'd you say? What'd you say?
I didn't say anything.
Yes, you did. 128.
Oh.
milliseconds would be the time per, I should call it. This is the time per revolution. And we're trying to get it from time to speed. Yeah, you're still milliseconds. So, but this is the time per revolution. Not yet. First of all, we can take the reciprocal of it. What's that? 7.8 milliseconds per revolution. Oh, I'm sorry. That's not millisecond, yeah. Revolutions per second. And then we multiply it times 60. Something's going wrong. Oh, this is 7.8. It's not 7.8 milli. It's 7.8. I can't take the reciprocal of 128 milli and come up with milli, right? And then we multiply this times 60. So this guy here is screaming. What are we doing? No, it's not screaming. 68 revolutions per minute. So what we just did is we had to go through two transfer functions, right? You understand? Because we had to go from time to speed, but our speed we came up with revolutions per second, and then we multiplied that by 60 to get it to our revolutions per minute. So how you go from the physical over to the electrical, that is the transfer function. That's what it is, guys. So we did it on a pot. Y'all did it. I had to do it all the time. So we had a pot that we came over here. And we're putting volts in, 10 volts in. Right, you understand. And then we're getting degrees out. And we said we had a 350 degree pot. I think ours turned out to be 300 or 320. So I'm getting degrees out. I'm putting what in? Volts in. Okay, so our transfer function is out 350 over n, 10. Okay, so that would give us what? Yeah. I'm sorry. Oh, I'm sorry. That is backwards. So we're moving this a certain, thank you. That is a certain amount of degrees, but what are we getting out? We're getting volts out. Sorry. Yeah. Thank you. So my transfer function would be equal to 10 divided by 350. Because what are we going to get out of these things? We got two things we normally get out of these sensors. What's the two things we get out? Volts or current. Volts or amps. So this is going to be milliamps over something, volts over something, and it all depends on how we set the span of the pot, right? And then we get our transfer function. What's our transfer function? So this is volts, this is degrees. So what's our transfer function? Yeah, 28.5 millivolts per degree. Now I know that, I can say, okay, what would my output be at 50 degrees? So V out would be equal to 50 times 28.5 milli, milli, and then this would give me what volts I get out, right? Understand? But once we know the transfer function, then we can figure out how the sensor actually works. If I don't understand the transfer function, so if I bring an analog input into a PLC, first we need to know the resolution of the A to D converter. The A to D converter on the 1100 is 1023. the 10-bit A-to-D converter. So what I would do is I would take my input voltage and I divide it by 1023, and that would give me the number of millivolts per input, right? You understand? Then normally what we have to do, we have to scale it, right? Y'all know what we mean by scaling. We have to take 1024 and make it mean something, right? Y'all understand? So we might need degrees. Well, I'm getting volts in, but my program needs degrees. So then we would know our transfer function, and we can scale that 1024 over to what it's supposed to be, right? That makes sense? So if it comes in and gives me, 5.6 volts on the output, it would give me 15.73 degrees. That's what the scaler would do. It would actually tell me what that means. Or temperature, and stuff like that. So I'm playing around with that with the Siemens PLC, and I'm trying to show you. So this is the transfer function. What's the transfer function? The transfer function gives us what? The correlation between the output and the input. So now I can bring temperature in and I can get volts out, right? You understand? I can bring speed in, I can bring speed in, I can get volts out, right? I can get speed in or bring counts out. Incremental encoder to get speed has got to count these things, right? So in the PLC it would be a lot easier. So we don't deal with time, we deal with the number of counts. So if I can count these pulses for 1 second, I understand that. And then take that count and multiply it by 60, then I got RPM. So PLC programming is a little easier. So we use this example because this is the one they use on the Siemens level 1 test. Well, PLC is a little easier because you understand what I said. Well, what can I do? Yeah, I can enter in a program, and I can count the number of pulses in a minute, and I can divide that by the number of pulses per revolution, and then I can multiply that by 60, and I got the time. So you can do one formula. So I'll show y'all that on the Allen Bradley. I think I brought a 11 over here, and I got a program that shows you how to do that. The Siemens is a little easier because you can make its high-speed counter measure frequency for you. It's really cool. So, really cool. Allen Bradley's. I don't know if the 5000 do that. So any more questions, guys, on that review?
Well, I'm looking at that up there, and that is exactly what we had in the
First lab. Yeah, that's the transfer function, and that's what I call it. In fact, that's on the slides. If you go back to the slides for the first class or second class, we call it a transfer function. And a transfer function is where we'll figure out what we get out for the physical quantity we put in. So what does a sensor do? Takes a physical quantity, right, you understand, and converts it over to an electrical equivalent. So I'm trying to figure out what that electrical equivalent means. If I don't know the transfer function and I measure the output of a sensor and I get 6 volts, what does that mean to you? It's a temperature sensor. What does that mean to you? It means absolutely nothing, right? Unless I knew 6 volts equals to 130 degrees, that's where it comes into play, right? You understand that? So that's what it means. So if we get the data sheets on the sensors and we look at the input voltage, and then we can take that input voltage and get the maximum output or the range of the sensor, then we can calculate what we get in. And then when I bring that into my control circuit, then now that voltage or that current means something to my control circuit. Right? You understand? So in your house, if you got a thermostat on your house, what does that thermistor do on your thermostat? It gives a voltage that represents a what? A temperature. But when you go over there on your control, you don't set a voltage, you set a what? You set a temperature. Well, if it didn't know what 30 volts was, of course it's not 30 volts, I don't know what they use in there. But if I didn't know what 4 volts was, then it would mean nothing to the control circuit. So whoever designed that thing And if I go in and my thermistor goes out and I put another thermistor in there and it's not the same one, what did I just do? I screwed up my transfer function, right? So, and that's built into the little controller, so I wouldn't think you would be able to reprogram. So, any more questions, guys? Speak now or forever ask you hold your peace. Right?
Well, on the study guide, terms. I don't remember the term capital ADD currently. Add currently.
Oh, that's my note. If it's an uppercase, it was telling Rich to add. I believe you. You don't have to bring it up.
Y'all didn't see that?
Yeah, I saw it. I did.
What is the current loop?
4 milliamp.
Well, that's one. There's several, but the standard is 4 to 20 milliamp.
Okay, I got it. You know, I didn't look at this stuff.
Now, we did talk about current loop, so tell me, what advantage does a current loop have over a voltage? No, it's not both sides. I mean, that's a good point, but it's not. The problem we have with voltage, what's the problem we have with voltage? Yeah, it maintains over. So when you say it's not precise, we can make it very precise, but the problem is over here I'm going from 0 to 4 volts, and over here I'm getting 1 to 3 volts, right? You understand? It's still giving us the same resolution of so many counts, but what happened is over here 4 volts meant maximum output, and over here I'm only getting what? 3, right? You understand? So voltage can be it can be really precise. It's just that we have problems maintaining voltage over distance. Now, of course, I is equal to V over R. So the way these current loop transmitters work is it has a range of voltages over here. Let's say it goes up to 30 volts. And as long as it's below 30 volts, it's going to automatically shift the voltage to transmit 40 milliamps for a 0 and 20 milliamps for whatever it's supposed to put out, right? You understand? If it's digital, 4 milliamps would equal a 0 and 20 milliamps would be equal to 1. If it was an analog input, then 4 milliamps would mean the sensor is measuring 0, right? And 20 milliamps would mean it's measuring its maximum range.
That's the current.
Yeah, but let's say if I had 100 ohms right there, my wire was 100 ohms in the system. Well, it would come up here and it'd say, well, V is equal to I times R. Well, it would come over here to say V times, let's do the low one, 4 milliamps times 100 ohms. And that's what the amplifier would output. Whatever voltage you come up to, that's what the amplifier would output on the left-hand side. Well, let's say something happened and this went up to 250 ohms. Well, this is what we call a constant current source. What's it going to do is it's going to automatically raise its voltage to keep the same current flowing, no matter, as long as I don't if I don't exceed the range of the current amplifier. If the current amplifier has to get up above what? Yeah, 30 volts, it can't do that anymore, right? You understand? It's just like your ohm meter. Your ohm meter is this guy right here. It's a constant current source. People don't understand that. So what it does is when you put your ohm meter across a device, it's got a constant current source. It outputs like 1 milliamp. You can measure that. And then it raises its voltage until 1 milliamp flows. And then it measures the voltage. But it don't say this is the voltage. It says it puts it up as ohms, right? You understand? So your meter is a constant current source. It does it. And you can put it across any resistance, right? Until it raises the voltage up as high as it can, then it says overload, right? You understand? And then it'll shift over to a different range. It shifts another resistive circuit in there, right? You understand? And that's the way your digital meter works. So what this means is I can basically ignore the resistance of the wire. As long as it's not too long, or as long as if I do good termination and if I do good splices, and I don't deliberately, if a wire breaks, it's screwed anyway, right? You understand? Because the output would go up to 30 volts and then it would do that. Another thing, EMI cannot generate a current. If we don't have a bunch of loops of wire and then hook them all in parallel, EMI cannot generate a current. But it can definitely generate a voltage, right? You understand? So we have another problem with using voltage, is that it's susceptible to electromagnetic interference. Current loop is basically immune to electromagnetic interference. So you're going to run into current loop a lot. You get out in these big noisy industrial environments, you're going to run into EMI a lot. Current loop a lot, except for lower plants. Older plants. You're going to run into them a lot. Because why? Number one, they're almost immune to the length of the wire, right? You understand. And another thing is they're basically immune to what? EMI. Now what's happening is we're seeing a resurgent. Because originally what we did when we sent voltage signals, we would come up here and we'd establish a common and we'd send it down the wire. And the common was also a reference to ground. Well, what would happen on this is that when voltage would come through this, it would generate a pulse into that, but it can't generate a pulse in the ground because that's what it's referenced to, right? You understand? And so what we would do is we would shield this, we'd run wire around it, copper, we'd shield it the best we could if we wanted to use voltage. Then they came up with something called a differential interface, which we come over here and we use a differential amplifier and a differential receiver. And what they do on this is they send signals, and I'm going to use digital because it's easier to draw. They send two signals and they're 180 degrees out of phase. Now what a differential amplifier does, it only amplifies signals moving in the opposite direction. So if it sees anything moving in the same direction, it ignores that. It's called common mode signals. It has a real high, what we call common mode rejection ratio. So what happens is if these wires, they're basically, we use what we call twisted pair wires. So these wires are basically wrapped together. So what happens, if a signal comes through this one, it induces a common mode signal in both of them. And what does this amplifier do right there? It rejects common mode signals. Now this is what everything's going to.
Don't have ground. It's not ground.
It's not grounded. These guys are not grounded. How do we get current flow? Well, the signals are always what? 180 degrees out of phase, yeah. So if this was an analog signal, then I was sending it on one, on the other one I would be sending that. So we can send analog on differential input signals. We can use digital on differential signals. It's going to use twisted pair wires. So if you ever open up a wire cable and the wires are what? Twisted together, then you know that's differential. And then we got two types of twisted pair. We got UTP and we got STP. Y'all know what those are? Yeah, shielded and unshielded. In industry, they'll add a second layer. They'll put a shield around it. And so and that way, it'll run. Ethernet is differential interface. USB is differential interface. So we can run these USB cables a pretty good distance, right, without worrying about picking up stuff. It would amaze me if your cell phone is serial. It's probably what the cable that you transfer information with. Also use it as a charger cable. There's probably 100% chance that uses different. It's unshielded too. They don't. So USB's differential interface. Ethernet's differential interface. So a lot of industry is going to Ethernet to hook things together. I was in the industry 4.0 when they started talking about the smart connection of everything. Everything communicates with that. If we got smart devices and it's connected to the internet, which makes it dangerous, then people that's not even by your computer can do things without even coming in. You know, used to, if you had your technicians couldn't fix something, then they would have to call somebody in. Now what they usually do is they call them on the phone and they connect to your network as well. Yeah, with phone. That does me too. We had one guy, I think he was working at Mercedes, and they was out there working, and all of a sudden this thing started over here, and I come find out that's what was happening. The guy was out there playing around with one of the programs. But you can block that. You can give it security, but you're always going to run into idiots out there. It's just like here. You know, they'll send a blanket email out to Lawson State, and they'll say, click on this link, and then we have people that's got doctor's degree here. They'll click on that link, and it'll download our whole email server to them, and then we'll start getting junk mail, thousands of junk mail. They'll start popping in because people sell those things. They send you people will send you an email. You got to watch out for this, and they'll put a link. Well, not the email is not the problem. It's those links inside the email that people open, right? Yeah, they'll send you that. They'll say,
email. I keep getting an email every day. Your name's been added to this.
That's me. Anytime I add you to a Remind class, it's going to.
No. I've had it. Some group that want to put you on there. College list.
Oh yeah, you got to be careful.
Yeah,
so any more questions, guys? So current loop, we talked about it. So I did add current loop, by the way.
Talk about this one is it's like a comparator.
We use a comparator to it's not a comparator. We use the output of it and usually bring it into a comparator. So what a Wheatstone bridge does is it allows us to set references, right? You understand that? We allow these resistive elements. First of all, normally if we got a resistor, if we got a device that gives us a resistance for what it measures, and what have we talked about? The only one we've talked about two, I think. We've talked about a photoresistor. And then we talked about that's the only one we talked about so far. We got thermistors, we got different things that varies their resistance for what they measure. But the problem we have is that they always have a resistance. So what that means is, how could I come over here? Let's say I take the output of my photo. Yeah, we can set the scale, right? You understand? So first of all, if there's no way in the world this sensor right here would mean anything to me, because how can I get an output on it? If I came over here and tried to get voltage out right there, what would it always measure? It's going to always measure the source. So at 5 degrees, it's going to measure the source. At 6 degrees, at 100 degrees, it's going to measure the source. So normally what we do is we'll come over here and put a resistor in series with it, a fixed resistor, and we can swap this around, guys. So the sensor might be up here. It depends on how you want things to move. Okay. Now, if I take my output right here, then if on this one, if the resistance of the sensor goes down, the output voltage would go down. If the resistance of the sensor goes up, the output voltage would go up, right? Y'all understand that? But at whatever it's trying to measure, it's still going to have a resistance. So it would always give us an output voltage. It allows you to establish zero. It allows you to do any other things to set references. So now it means something, right? So now we can make it mean something. So we put it in a bridge, and then we can calibrate it. And of course, the ratio between the two sides determines if it's balanced or unbalanced, right? So if the ratio of the two sides are the same, it means it's balanced. If the ratio of the resistors are different, it means it's what? Unbalanced. And they don't have to be the same. So this could be 1.5K, this over here could be 15K. And this over here could be 10K, and this over here could be 100K. And then this guy would be balanced because the ratio is the same, right? You understand? So it's up to you. How do you calculate the ratio? You can take this one over this one, but if you take this one over this one, and then over here you got to do what? This one over this one. If you do this one over that one, then over here you got to do this one over that one. If you come up and get the same ratio, it means it's what? Balanced. If you come up and get a different ratio, it's so what we can do here is we can make maybe these two right here could be what? Variable. And then of course we're taking our output right here, right? And we're looking for what here? We're looking for volts. So if we put a voltmeter there, the ratio on the left, if we're using the bottom one to the top one. So if the ratio on the bottom was less and this was more, then it would give us a minus, right? If it may be a plus or not. So not only can we set 0, we can also get an indication if it goes below 0, right? A good example is the centigrade scale. So we can set 0. If it goes minus, it means it's below freezing. If we get plus, it would mean it's what? Above freezing. So we can set 0. We could do it with the Fahrenheit scale too, but it would be hard to get a 0 in a Fahrenheit. It's real easy to get a 0 in centigrade because I can just take my sensor and immerse it in a glass of ice water, right? And then stir it up real good and put my sensor in there, and that would give me a reference of 0. If I did it on Fahrenheit scale, somehow I'd have to get what? 32 degrees below, I'd have to go to 0, and that would be a little harder. So we could adjust it and say, okay, this would be equal to 32, but it would be a little bit. So that's why so just about any sensor that's going to give us a voltage relative to a resistance, we want to do things with it. We don't want to modify it before it gets to our computer, and we'll put it in a bridge. Now on scales, we have a thing called a load cell. We'll talk about that later, but it's a Wheatstone bridge like this. But we don't use it to set 0. We set 0 in the scale. Does that make sense? So we'll go into the scale, and then we'll take all the weight off, and then we'll go in there and we'll say that this output in the computer, we'll say this output is 0. Now while we do that, we had the same indicator. We had the same indicator that would run on different scales. They'd have different weigh bridges. They would have different load cells, right? You understand? So we had to do it that way. So we calibrated the actual indicator to what the load cells gave us. But we do a Wheatstone bridge, and we'll show you why when we get there. We use Wheatstone bridges a lot. In fact, there's one on the test. Are we okay? Any more questions? I'll look at it. I'll decide when we're going to start the test. I need to look at the number of questions. And like I said, where I was at, trying to get all our computers loaded onto our new domain. It's still not quite right. I got one down there that won't find the domain for some reason. So let's go ahead and let's go to lab, guys. Work on lab until